All right, welcome to statistics. We're going to talk more about probability. Once again, one of the underlying aspects of statistics is having a good, solid foundational understanding of probability. That's a long sentence, I guess, isn't it? But the idea being is when we start getting into other and deeper concepts within statistics, we have to have an understanding of what that probability means. And manipulation of probability models helps us with other aspects of statistics as well. One of the things I want to look at is another example involving probability, namely when we have events that are kind of compounding events, if you will, where the events, and we'll talk about whether these are independent or non-independent events, and whether they're disjoint or not, non-disjoint, and then also what rule we're going to be dealing with for those events to occur. Okay, now so let's pay attention to a couple of pieces here. So let's just say that I want to know what is the probability of a particular event occurring. Okay, so if I say the probability of, let's say the probability of event A and event B, or A2. We'll call it A2, and I'll explain why it's A and A1 and A2 here in a second. But we want to figure out what those probabilities are. Well, in this particular event, assuming the events are independent of each other, it'd just simply be the probability of A sub 1 times the probability of A sub 2. All right? And that's how we'd figure those out. So if we had multiple independent events, and that's the kicker here, is it has to be multiple independent events. So A sub 1 and A sub 2 and A sub 3. Well, guess what? That'd just be the probability of all three of those multiplied together. Again, assuming these are independent events. If they're not independent events, it does change what we need to do a little bit. Okay? So let's just say that we're talking about during World War II, flying a bomber across the English Channel and then into Europe and dropping bombs off to try to stop the Nazis from building weapons and building machineries and things like that to help them with the war effort, essentially trying to destroy their war machine. The individual probability, the probability of a particular pilot surviving a particular mission, we'll just call that P of A, was roughly 95%, or 0.95. Remember, we can write probabilities between 0 and 1, and then we can also think about them being a percentage as well. I mean, 95% of the time, the pilot would come home safely, okay, be uninjured. So that's a pretty good likelihood that you're going to go out and come back every single time. So what's the probability that they could fly 3 missions? Well, 3 missions is the event that we have up here, which means that you would then need to do 0.95 times 0.95 times 0.95. Or you're talking about it being 0.95 raised to the third power, which in this instance actually turns out to be 0.857, which again is not too bad. So just running 3 missions in a bomber, you have a pretty good success rate for survival. So what if you talk about the average number of missions, which was 30? Well, then that would work out to be P of A sub 1 all the way to P of A sub 30. So you're talking about this being 0.95 to the 30th power, because you're going to multiply 0.95 times itself 30 times. And in this instance, it actually works out to be 0.2146. So as time goes on, the probability gets smaller and smaller and smaller, because you are taking values less than 1, greater than 0, multiplying them together to get that outcome, which means that the survival rate, or the probability that you would survive 30 missions without injury, a life-threatening injury that would end either your service in the military or end your life, was 21%, or 0.21. So it was actually, if you want to put this on the scale, it was highly unlikely that you would complete 30 missions. So the individuals who did complete 30 missions had a very low survival rate. further you get in closer to that 30 mark, the lower it gets. And if you were to go beyond 30, it was even lower than that. So you're talking roughly a fifth of the pilots or those bombers would survive 30 missions, which gives you a lot of interesting information to deal with from a statistical standpoint. If you're talking about 30 missions, you have 1/5 of the fleet that you started with. That tells you that you need to replace 4/5 of the fleet every 30 missions. That kind of gives you an idea. If you're running one mission a day, every 30 days you're going to be needing to pump out 4/5 of your fleet. So if you're sending, let's just keep the problem simple in terms of fifths and things like that. So if you're talking about 20 planes, okay, and you know that 1/5 of your planes are going to survive 30 missions. So at the end of a month, you're going to have 4 planes. So that means you need to manufacture 16 planes every 30 days, which is a pretty daunting thing. So how often can you run those raids and be able to maintain your fleet at the same level? If you can't produce 16 planes in 30 days, then you're going to need to extend or lengthen the amount of time between missions. You can't run 30 missions every single day and expect to still have your entire fleet or a substantial part of your fleet at the end of that time period, because you're going to be losing more and more of your fleet, statistically speaking. Now, of course, the other part of this is the idea of the randomness that plays into this. And also keep in mind, let's talk about the independence of this as well. Okay, we'll talk about both of these in turn. Randomness. Randomness means that it is, by its nature, is unpredictable. Okay, there is no order to the next outcome. Okay, so even though there is a probability that of surviving a particular mission, and then we figured out the probability of surviving 30 missions, really ultimately each individual mission, this mission, mission 1, mission 2, mission 3, mission 4, mission 5, all the way down the line, are independent, because they're not relying upon, or are they relying upon, surviving the previous mission? Right? So assuming you've survived the previous mission, what's the probability of surviving the next mission? Well, those events are actually completely independent. It's like flipping a coin, 50-50 in both directions. And some of you may be wrapping your head around this thinking these events aren't independent. Well, they are independent and they are random, because there's no order to which whether. You could go on the first mission and not come back. You could go on 1,000 missions and come back. That is the idea behind it being random and it being independent. This is not terribly random. 0.95 puts us in a position where this is not completely random. There's a fairly high likelihood of surviving a single mission, but still there's a 5.05 probability of not completing that mission. The idea of randomness means that that could still occur. So it could still happen even though the likelihood is high that you're going to survive a single mission. So going all the way back to the 30th mission, you're about to go out for that 30th mission here. What does probability tell us? What does independence and randomness tell us about this last mission? What it tells us that last mission has a 95% success rate. Finishing 30 missions has a success rate of 0.2. Just kind of think about those. Pause the video for a minute if you need to, but think about what that means. Okay, it kind of seems a little weird. Is that the 30th mission? That's a 90.95 probability that you're going to be successful on that last mission, right? On the 30 missions, not 30th, but 30 missions, you have a 0.2 success rate. Okay, but the last mission itself is still a 95% success rate. So when you actually you've completed the 29th mission and you're about to go out and complete the 30th mission, there's no the truth of the matter is you still have the same probability of completing that last mission as you did completing the first mission. 0.2 is not your probability of finishing that last mission. 0.2 is the probability that you would finish 30 missions. Finishing that last mission only has a probability success rate of 0.95. So that's the difference between these processes here. These are still random events in that you still have some possibility for failure, and you still have, in this case, a lot of probability for success. They're independent, meaning that the fact that you were successful or unsuccessful on the last mission doesn't necessarily have a direct effect upon the success of another mission. Now, the difference between this situation and, say, real-world scenarios, and this is what some people might be thinking, is that there is this carryover. In basketball, there's actually a phenomenon called hot hand. And the idea behind hot hand, for those who are familiar with basketball, is that you have a player who gets on a streak of some sort. Okay, they make a lot of shots and they make the first shot, and all of a sudden they've made, say, 5 in a row. Okay, I grew up in the late 80s, early 90s, and I got to watch the Bulls play and watch Michael Jordan play. And I remember after a game, him commenting about how he'd look at the goal, and the goal looked like it was 10 feet wide, and he just couldn't miss because he had this phenomenon called hot hand, meaning that making a previous shot is going to have an effect upon making the next shot. That has to do with something outside of math and probability, and more to do with skill and confidence within that particular activity. Okay, so the same thing would be true about the pilots. When you're on your 30th mission, you have more skill, you have more experience, maybe you also have, maybe you have more nerves, but if you're assuming you're doing things the same way, you're going through processes, you're doing things you normally would do. One of the differences is the more experienced pilots would always be near the front of the fleet instead of the back of the fleet, and that would change who's surviving those runs. In the hot hand scenario, you are talking about there's a definite skill and confidence level that occurs. Making a shot, making a second shot, making a third shot, you start to really get into what's called the zone, right? And which has nothing to do with probability models. And that is all a mental aspect of the game that affects your skill and confidence to shoot the basket. Because it's all muscle memory at that point. That's a skill level. And when you do that, the amount of randomness involved goes down. Okay, it changes things. And in this instance right here, you're also talking about the independence of those events is also going down. So the randomness and the independence is going to decrease because this is a skill-based activity, as opposed to, say, flipping a coin, which is not skill-based. So it kind of brings up this idea of what is called either positive or negative recency. And the idea behind recency is that, I spelled that horribly, sorry about that. Anyway, recency is this idea that the most recent events are going to affect the next events. Positive meaning that positive outcomes occurring recently are going to think that positive events are going to occur or continue to occur. Negative recency means, well, a lot of positive events have occurred, so negative events are going to change. What it basically means is positive recency makes you think that whatever has been happening is going to continue to happen. Negative recency makes you think whatever has been happening is going to stop happening. It's the same idea in baseball when they say someone's due for a good game because they haven't hit the ball in a wall. It's that same idea. I'm bringing this up because this topic right here, this hot hand idea, this idea of recency within a sport or skill-based activity is different and separated from this idea when we talk about strict probabilities. These probabilities that we're talking about with the pilot and whatnot, these are what we refer to as ideal situations as opposed to skill-based activities, which is the hot hand phenomenon. So the skill-based activities. And the primary difference here is that when you start building into a skill-based activity and you start dealing with real-world scenarios, this idea of randomness disappears and independence also disappears. So the success of the 30th mission might actually be dependent upon the success of the previous 9 missions, or maybe even just the last one. There's even documentation of this that exists within motorsports as well. Someone gets into a bad wreck, it takes them a while to rebound and actually start performing better, just because their confidence is shattered, literally, because their body might have been shattered. Okay, so there's a lot to be considered there. So in when we talk about probability within the world of statistics, we are always referring to the ideal situation, But when we start talking about and summing up what's going on in the real world, we want to make sure that we are paying attention to other aspects of things like this hot hand phenomena and how that would affect outcomes, which is the primary issue of what holds us back from being able to say that an event is most definitely going to occur, like this idea that the 30th mission has a 95% success rate. It doesn't really mean that 95% of the pilots that go out are going to come back unharmed. It doesn't mean that 95% of the time I go out on that particular event that I'm going to come back successful. Individual pieces are going to change. So we need to be very attuned to talking about ideal and also discussing those real world applications or events or outcomes as they may be based upon actual skill-based activities. So a lot of times when we do studies, we're also looking at, say, how a drug performs. And in that case, we'd have ideal situations, and then we'd have the real-world scenario that goes kind of back to this idea of the hot hand thing. And how does that drug really interact? If you're talking about drug trials, those are under normally extremely controlled environments, and I even knew an individual whose child was going through a drug trial, an experimenter drug to deal with anxiety years and years ago. And they were able to fine-tune her medicine down to the 10th of a milligram. And they were actually able to fine-tune her medicine to the point where she had almost no side effects, and the anxiety issues that she was dealing with completely disappeared. And then when the drug was approved by the FDA, it was put in pill form, and it was in 5 milligram tablets. And at the time, the young lady was taking 8 milligrams or 8.5 milligram tablets. So 5 was not enough, 10 was too much, 5.5 is what she needed, but she could no longer take that. So that kind of goes back to this idea of the ideal situation versus in the real world what really happens. So when we conduct studies, we want to make sure that we're doing that and we're not introducing confounding variables that would make this real world application that much harder to deal with. All right, I hope this was useful. I hope you find that statistics is enthralling, or at least at the very least makes good numbers, right? So take care and have a good day.